The p series with p equals 1 is called the harmonic series. The sum from n equals 1 to infinity of 1 over n. So that's just 1 plus a half plus a third, etc. We learned that this series is on the boundary between convergence and divergence, and in fact, this series actually diverges. So it's interesting to look at a second proof that this series diverges. We can do that if we write this series as follows. We write it as 1 plus a half plus a third plus a quarter. So I'm going to group terms like this. This has one term in it, 1/2. This has two terms in it, 1/4. Two terms in it, 1/3 plus a quarter. So the next grouping, I'm going to double the number of terms, so we'll have 4 terms. So the next grouping will be 1/5 plus, and we can go up to 1/8. Okay, so 1 term, 2 terms, 4 terms. The next one will have 1, 2, 4, 8 terms. So we'll have 1/9, and then it will go up to 8 times 2, which is 1/16, and so on. So we're writing all the terms. So we start with 1 term, then 2 terms, then 4 terms, and then 8 terms. The last term in the parentheses here will be 1 over powers of 2. So 1/2, 1/4, 1/8, 1/16. We can say that this series here, which is the harmonic series, is then greater than 1 plus our 1/2. And we can replace 1/3 by something smaller than 1/3. That would be 1/4. 1/4 is smaller than 1/3. So this can be 1/4 plus a quarter. And then we can replace 1/5, 1/6, 1/7 by something smaller than them. We can replace them by 1/8. So that becomes 1/8 plus ... plus 1/8. And finally, we can get 1/16 plus ... plus 1/16. Okay? There are 2 terms here, both of them a quarter. There are 4 terms here, all of them 1/8. And there are 8 terms here, all of them 1/16. And we keep on going. So each of these parentheses terms then are equal to 1/2, right? A quarter plus a quarter is a half. 4 1/8 is 1/2. So this is equal to 1 plus a half plus a half plus a half plus a half. And you see that we just keep adding 1/2. And that obviously goes to infinity. So that goes to infinity. So we have the harmonic series then is larger than infinity. So the harmonic series diverges. So that's another proof of the divergence of the harmonic series. Okay, interesting. We can change this series slightly and end up with something that converges. That's called the alternating harmonic series. Alternating harmonic series. And that's the series 1 minus a half plus a third minus 1/4 plus a fifth minus 1/6. And you see the pattern here. It's called an alternating harmonic series because we have a +1, a minus a half, a plus, a minus, a plus. So we're alternating the signs. To see why this series converges now, we can look at a graph. So let's have a look. So here's our graph. I'm showing you now that we're starting at 0. So this is the 0 point. And we're starting with 1, so we go to 1. So this is the 1 point. And then we go back a half. So we go forward 1, back a half, forward a third, back a quarter, forward a fifth, back a sixth, etc. So you see that we're moving larger, smaller, larger, smaller, larger, smaller. And eventually we're going to converge to some point here. And that's why the alternating harmonic series converges. Later, I'll show you that this number here turns out to be the natural logarithm of 2. Rather crazy result for the alternating harmonic series. There's some mathematical detail here. We won't go into it in this course, but I should mention it. There's something called absolute convergence. So a series is absolutely convergent if the same series where all the terms are absolute value, so then all the terms are made positive, then we say that the series is absolutely convergent. So if we look at the alternating harmonic series, if we took the absolute value of each term in this series, then we get the harmonic series, which we know diverges. So we say that the alternating harmonic series is not absolutely convergent. It turns out that series that are absolutely convergent have very nice convergence properties, and we'll be discussing that a little bit later in this course. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video.